Good. So I hope you can hear me. I need time, sorry. To measure time, I mean. Okay. So 3 allocators walk into a bar. My name is Christos Lamprakos. I'm a PhD student at the National Technical University of Athens in Greece, and also KU Leuven in Belgium. Currently, I'm a research intern at IMEC at the Compute Systems Architecture Department, also at Belgium. And today, I have the great pleasure to talk to you about the unexpected efficiency of bin packing algorithms for dynamic storage allocation in the wild. Before I commence, when I was rehearsing this talk, I hadn't seen Dr. Maas's keynote talk. Expect some overlap. Don't expect I have stolen anything. It's a very exciting convergence, actually. And that said, I will begin with the motivation and also the main contributions of the paper. So we know for a very long time that the main enemy of any allocator is memory fragmentation, at least from first principles. We know it's hard to deal with because it depends on the interaction between workload and allocator design. And we also know it's hard to measure, especially online, because, of course, we cannot know the future. But despite the central role of fragmentation, DSA research has focused in the past 3 decades on performance mainly, which makes sense due to the emergence of parallel workloads, very important problems to treat, like thread contention and stuff. But also due to some historic papers, actually, that claim that fragmentation has been solved for most cases. However, reality contradicts itself, and we also have allocator designers having a hard time to actually define fragmentation, and a good example is Jason Evans in his 2006 paper about gemalloc. We also have new definitions of fragmentation, like a recent ISMM paper by Dr. Maas et al. And meanwhile, modern workloads are massively deployed on the cloud. We have non-volatile architectures emerging, which kind of not let us afford considering memory, even virtual memory, an infinite resource anymore. So if fragmentation depends on the interaction between workload and allocator, then the big picture of my PhD essentially is to capture this interaction by utilizing existing formal treatments of DSA based mainly on 2-dimensional rectangular bin packing, aka 2DBP, which of course are offline. They are viewed as NP-hard algorithms and are also targeting makespan, which may not make sense in the first glance, considering Linux demand paging. But, and you will have to just trust me on this, there is a sister work to this intellectual abstract, you can check it on arXiv, where we show that it is possible to construct this representation for real workload allocator pairs, and it is possible to define a fragmentation metric on top, which very often correlates with peak RSS. Ergo, those representations have information. Ergo, we can use them for analysis, the first example of which is the paper today. And in case you are curious, an example of how those placements look like is this figure. On the vertical axis, we have virtual addresses. On the horizontal axis, we have logical time. This is just a text-to-speech engine. We will make a toy example in the next slide, so feel free to delve more into the full paper if you like. Our main argument is that if it makes sense to view allocators as 2DBP agents, then we have some interesting side effects we can check research-wise, the simplest of which was actually proposed to us by the ISMM reviewers, which is to compare allocator placements with Robson's worst-case lower bounds about the makespan of placements. But if you follow this to its logical conclusion, then you think that you cannot avoid putting allocators against some offline oracle, some 2DBP offline algorithm that computes approximately optimal placements, and see for particular workloads how far an allocator achieves its makespan from the ideal one. So this is basically what we did here. We have a first implementation of the state-of-the-art in offline DSA. We include the lessons learned while we were trying to implement it. We also have a comparison of 4 modern allocators across 8 modern workloads. with respect to makespan against Robson's worst-case lower bounds. And last but not least, we have an analogous comparison, this time not with Robson, but with the DSA state-of-the-art that we implemented, both in terms of makespan and a fragmentation definition that we introduce. That said, let's move with some background. As I promised, we will construct a toy representation for a very small sequence of requests. We start with a two-dimensional address space on the vertical axis and logical time on the horizontal one. And we go step by step, receiving requests. First, we have a malloc request of 1 byte. We assume the allocator decides to put it on address 01. And so a rectangle is created at address 01 with height 1. And time also progresses forward by 1 byte. Then a second allocation request comes. The allocator this time decides to use virtual address 3, and new rectangle is created. Time progresses forward. Then the block A is freed, so we just close this rectangle. Time does not progress forward. It's just how we decided to define the dynamics of logical time. Then a new allocation request comes, 3 bytes this time. The allocator decides to put it at virtual address 0. We create a rectangle, extend the rectangles that are still live, the objects, and then to free request comes, and we have the representation for this sequence, which, in our opinion, very well captures the interaction between workload in the sense of the series of requests and the sizes, and also the decisions that the allocator took. And in case you were wondering about the red areas, they are, in our opinion, the sources of fragmentation. They are unused spaces in the virtual address space times the time. Of course, we focus on the external kind of fragmentation because we are interested in placement. So we see the gaps between blocks. We also focus within virtual page boundaries because we're interested in Linux VM. We have no guarantee that contiguous virtual pages are contiguous in physical space, so we are conservative on that. And within those page boundaries, we divide the area of the gaps with the area of the objects, and we have a first sense of a quantified sense of the fragmentation that this sequence produced. As regards the algorithm that we implemented, we will dub it BA from now on. It was published in STOC in 03. It's by Adam Buchsbaum et al. It optimizes, like all algorithms in this family, the makespan of the placement, the totality of the address range is used. And it gives a guarantee. It has an upper bound, which is defined by the maximum object size and the maximum amount of live memory in the same sense that Robson's bounds also function. The main idea is that it boxes objects in larger objects, let's say, and it places those groups instead of the individual ones. I will not go into any more details, but it is important that it imposes no restrictions on the input, so we can use it for any allocator workload pair. As regards our implementation, on the right, we have a very arcane figure that comprises, on the rectangles, the several corollaries and theorems that the original work had. It proves everything by construction, so implementing the algorithm actually amounts to implementing, to reproducing each construction proof in code. The circle boxes are the objects, the initial set of objects which go several transformations within the algorithm, and the final boxed and placed set in the end. Convergence of this algorithm was non-trivial. We had to do several adjustments. Encouraged by the reviewers of ISMM, we spoke with the original authors. Unfortunately, a lot of time has passed since then. One of the main authors, however, he told us that it's natural when you go from theory to practice to have to do some adjustments. And also note that the performance is unpredictable. The algorithm converges for 200K objects, but it leads to out-of-memory errors for 20K objects, so the topology of the objects has its role as well. And also some post-processing was needed. Again, feel free to check the paper for all the details. About the results now, all of our results will have the form of bar graphs. We have on the horizontal axis 8 workloads we took from openbenchmarking.org. We were very adamant about staying on real applications. We ran our experiments on a typical Ubuntu 20.04 machine. And for this first bar graph, as promised, we see the makespan of the allocator placements for each of the benchmarks normalized to Robson's lower bound. And as conventional wisdom already tells us, we validate that most of the time, most of the allocators vastly outperform the lower bounds of Robson. And the particularly outstanding case is glibc, which is consistently very, very much better than the lower bound. We tried to explain it by manually inspecting the placements, and we saw that glibc is very reluctant in employing sparse addressing, so it produces, by default, much tighter placements. For the second result, we move, instead of the allocators, we now have BA, the algorithm we implemented, and it was a kind of sanity check we needed in order to be sure that all the adjustments we made functioned and we have functional correctness in our implementation. Indeed, we see that all the placements computed by our algorithm implementation, they conform mostly, more or less, to the upper bound with the big O notation having been switched to a factor of 2. So this makes us quite confident that our implementation is correct. Then we have allocators versus BA with respect to makespan. Again, since BA optimizes makespan, it's natural for it to outperform most of the allocators. On the right is the figure that we already showed about the Robson's bound. A nice detail is that the trends on the left figure follow the trends on the right. So we use it to say that maybe this bar graph is a nicer bound, a more tight bound for allocator performance than the quite deprecated Robson's bound. Also, we cannot help but notice that glibc, which is online, it performs much better than our implementation, which works offline. And we had to explain it somehow. And we went back to how BA behaves with respect to its own upper bound. We saw that the degree to which it is outperformed by glibc is quite equivalent to the degree in which BA is defeated by its own upper bound. So it's quite evident here. You see that BA didn't manage to win its upper bound in this case, and it's much worse than glibc in this case, while for the system libxml benchmark, where BA is quite decent, glibc has 16% worse makespan. So this is an indicator that, again, however this BA behaves with its own upper bound, predicts how it will go with respect to makespan. And finally, this is the most counterintuitive result. Despite not being designed to minimize fragmentation as we defined it, BA produces much better fragmentation-wise results than almost all of the allocators, glibc again being the exception. And again, this happens to the inverse degree to which it is defeated by its own upper bounds. See, for example, here, the allocators memalloc, for example, has managed 0 fragmentation, while BA in the memalloc placement, it was quite bad with respect to its upper bound. So to summarize our findings, yes, allocators outperform Robson's bounds with respect to makespan. BA's own upper bound may be a tighter alternative as a lower bound for allocators than Robson's values, and also off-the-shelf GNU malloc is quite equivalent or better than BA in terms of makespan, and the degree to which this happens is predicted by BA's performance with respect to its own upper bound. And most surprisingly, BA 65% of the time is better with respect to fragmentation than conventional allocators, which are supposedly focusing on minimizing fragmentation. Again, how BA performs against its own upper bound is an indicator. Our conclusions are that we're totally in agreement with what Dr. Mas said about a new golden age of memory management. There are countless theoretical and practical crossbreeds that show promising potential for future DSA techniques. There are no silver bullets. Workload identity plays a huge role in understanding what allocator to use and when. And also, we think that in environments where memory is critical, you cannot avoid, most of the time, custom memory allocation policies. Now, to the giants that came before us, many of whom are in this room, and we are very honored to be here with you, and also to the reviewers, the shepherd of the ISMM, the PC, and especially Professor Erez Petrank for his very helpful replies while fighting towards acceptance of this paper. And to you and the speakers of today, I want to say thank you. 1 year ago, I wouldn't even imagine I would be here. It is an honor to be part of this convention. And remember that allocators are not alligators, so you can play with them as long as you are not in a production environment. Thank you. Why, sorry?
The compressed music looked very bad. Do you have any insights why that might have been so bad?
Yeah. No, I don't. But in the other paper that I mentioned, which is not published yet, compressed gzip was one of the cases where indeed fragmentation correlated with RSS. So these results are not expected to hold horizontally for any workload. This is the point, actually, that particular workload behavior plays its role. Now, what the explanation is, no, I cannot tell you.
Can I get benchmarks? Are they online?
Yeah. Openbenchmarking.org for Onyx test suite is the programming tool you can use in order to run very fast those benchmarks in your machine, yes.
Have you thought about threading and how that affects the choices?
All those benchmarks are single-threaded. We are currently running some new experiments with parallel applications in order to better generalize what we are claiming here, because, of course, it's a very small sample. The first results are promising, but I cannot be more open right now. Thank you.